Hello everybody, my name is Dennis Jacob. I'm a researcher at UC Berkeley, and I'm going to be presenting our work, PatchDEMUX, a certifiably robust framework for multi-label classifiers against adversarial patches. I did this work at Princeton with my co-authors Chong Chang and Professor Pratik Mittal. And so this is the poster for our work. This presentation is essentially going to be just a rundown of the poster for virtual attendees, so let's get into it. All right, some motivation for our project. Deep learning-based computer vision systems are vulnerable to adversarial attacks, and these are basically attacks where an adversary perturbs some region of an input image to cause misclassification. Chief among these are adversarial patches, which are basically where an adversary is restricted to a square-shaped or patch-shaped region of the input image. And these are important because these are physically realizable. Now, like I said, many systems, CV systems, are vulnerable to these attacks, including multi-label classifiers. And these are CV models which are tasked with recovering multiple objects from an input image. And one example where this is useful is traffic pattern recognition in autonomous vehicles. Now, defenses have been proposed for the adversarial patch attack. Specifically in the field of single label classification, where you're trying to recover at most one object from an input image. And many of these defenses are what are called certifiable defenses, which give some provable guarantees against patch attacks. So if you have some image in the single label classification domain, you can run some algorithm that gives you some guarantees whether or not it's secure against patch attack. Here's just a quick kind of example of multi-label classification settings. So here we have a car coming up to an intersection. It's tasked with identifying the traffic scene. Is there a car coming in from the left? Is there a pedestrian? So LC means car coming in from the left. Pedestrian is LP from the left. I notice here that the model needs to recover more than one object. There might be a car, there might also be a person, or maybe there's none of the above. And so this is a scenario where multi-label classification can be helpful. All right, so I mentioned that there are defenses that exist for single label classification, provable defenses that exist, but there isn't anything that exists yet for multi-label classification in the adversarial patch threat model. And so that's where our work comes in, PatchDEMUX. And the way we approached it is we decided we want to have something that's very flexible. And so we came up with a framework that can provably extend any existing single label classification method to the multi-label setting. And as a certifiable defense, it has provable guarantees on provable lower bounds on performance. And we tested with the current state-of-the-art single label defense and find that we can achieve strong robustness guarantees. All right, now into the background section. So we're first going to talk about the patch threat model. And as I mentioned before, the patch threat model is where an adversary has access to some small restricted region in the image, typically square-shaped. So you can see here's a mathematical representation. For some image X, the patch threat model means you can take some restricted region R and the adversary has full control over it. So a real-life example of this might be an adversary prints out a sticker and puts an adversarial attack on it. And so that would be an example of a physically realizable patch. And then you can put this in front of a camera or some other CV system and cause failure. We're now going to talk about certifiable defenses. So as I mentioned, these are a popular choice for defending single label classifiers against patch attacks. And certifiable defenses involve two key procedures. The first is the inference procedure. This basically runs at test time and is responsible for defense predictions. You can think of it as a drop-in replacement for the model. It takes the input image X and spits out the label Y. And the second procedure is the certification procedure. This is used for finding lower bounds of performance. It's not used at test time. It's only meant as a check on robustness. But it basically gives, for some input image X, it gives the lower bound of performance for the inference procedure regardless of any adversary. Input images that have some non-trivial lower bound are called certifiable. All right, so how do you create a certifiable defense for multi-label classifiers? You're going to need an inference procedure and a certification procedure. Well, the key insight of PatchDEMUX is that we can treat multi-label classification as a series of isolated binary classification problems. So recall that in multi-label classification, you're trying to recover a series of different objects. And so if you look at each object, each class as, whether it's absent or present, well, it's essentially a binary classification problem. And so we take advantage of this isolation principle for the inference and certification procedures. For the inference procedure, we essentially take the underlying single label certifiable defense and we apply its inference procedure to each class I in a series of C classes. And for the certification procedure, we take the underlying single label certification procedure and we apply it to each isolated classifier. You then accumulate all of these results, and we can basically then lower bound the set of true positives in a data point label. Once we have the lower bound of true positives, we can go further and bootstrap notions of certified precision and recall. Precision and recall are very popular metrics in the multi-label classifications community, so having a certified or robust equivalent for these metrics is very useful for our evaluation later on. All right, so I have a figure here which kind of conceptualizes our inference procedure. We take in some input image, and for each of the classes, we apply the single label inference procedure, and then we aggregate each of those predictions. Now notice here, if the SL infer, if the time complexity is say OFN, then it looks like we're kind of running a loop here. The time complexity for our multi-label inference algorithm is going to be scaling with the number of classes C. But it turns out in practice it's possible to take advantage of relatively negligible post-processing in the defense procedure, and in practice you can actually reduce the time complexity back to OFN, and more details are in the paper. Okay, so recall that certification is done not at test time, but it's done separately to find some lower bounds on robustness. And it turns out that in certain cases we can do better than our vanilla approach, and we call this approach location-aware certification. So essentially, when the attacker is limited to a single patch, we can try to return a vulnerability status array for each class that fails the vanilla single label certification procedure. And so I have an example here with this image where you have a dog, bicycle, and some people. And I made a vulnerability status array for each of these classes, so it's an example. And I've highlighted in orange the locations that I'm going to say are vulnerable to a patch. Now it turns out if you add all of these together, you can get this combined array where the maximum value corresponds to the location that an adversary should put a patch if they want to misclassify as many classes as possible. But notice in this case, the bottom left-hand corner, actually the people class is not vulnerable to a patch there. And so even if the adversary plays optimally, the people class is going to be protected. And so that's the basis for location-aware certification, where by generating these vulnerability status arrays, we can try to extract some residual robustness bounds due to the fact that different classes might have different vulnerabilities to patch locations. All right, now for some results. All right, so here are some of our results. So we initialized PatchDEMUX with Patch Cleanser, which is the state-of-the-art single label certifiable defense against patch attacks. And we tested on two popular benchmarks, MS-COCO and Pascal-VOC. So here I have some tables for the MS-COCO evaluations. You can see here on the left that when looking at clean performance, applying PatchDEMUX does not have a huge impact on utility. As you can see here, it's some chosen recall values. The precision doesn't drop too much when you add PatchDEMUX. This is average precision, so it's kind of the precision over a wide variety of recalls. And you can see here again that adding PatchDEMUX as an overhead doesn't have a huge impact on the average precision. How about robustness? Well, when we apply our certification procedure, we find that we get some non-trivial robustness. So the average precision is around 45% when we apply our stronger location-aware setting. Now, this is not as good as the clean setting, but we argue that since there's no existing baseline for multi-label robustness against patch attacks, we think that 45% on MS Coco is a good start. All right, here we have the associated precision recall curves. This is basically where you take the model outputs and you sweep them across a wide variety of decision thresholds and then plot the associated precision and recall paired. On the left, we have the clean setting, and you can see that in green, adding PatchDEMUX as an overhead doesn't detract too much from the overall curve. On the right, we have the certified robust setting, computed using our certification procedures. And we can see that we have a non-trivial curve for both the location-aware and the vanilla certified robust settings. Now notice that both curves are slightly convex in shape, and this points to some potential room for improvement compared to the concave shape of the clean setting. But we envision in the future with stronger single-label certification procedures that PatchDEMUX in turn will get stronger and have stronger precision recall curves for the certified robust settings. So in conclusion, we proposed PatchDEMUX, a new defense for multi-label classifiers against patch attacks. One key feature of our defense approach is that it can extend any existing single-label defense to the multi-label domain and provide provable guarantees as well. We hope that future work will interface with our framework, and our code is available at the following GitHub link. We would like to acknowledge our funding here, and you can reach me at this email address. And please feel free to read our paper online. It is on arXiv and will also be available publicly on the CVPR website. Thank you.